So today's topic is tune PostgreSQL for read and write scalability. So my name is Ibrar Ahmed. I'm a principal engineer at Percona. So I'm not talking about much of the detail about who I am. So I am working on software development since 1998-99, and for PostgreSQL, I'm working on the PostgreSQL core engine since 2005 and 6 when I joined the Enterprise DB, the big guy here who hired me in 2005 in Enterprise DB. He's here in Dennis. So I also wrote multiple books on PostgreSQL. So one of my books is also translated in Chinese and is very well received in Chinese language. So we are talking about the database performance. So when we are talking about the database performance, we need to think about first the database performance. Before that, we need to discuss the PostgreSQL architecture. And then we will talk about the PostgreSQL performance tuning and Linux kernel tuning. So that's the three parts: the architecture, the PostgreSQL tuning, the Linux tuning. So we will skip the database benchmarking, some kind of stuff, because we have only 1 hour, so we cannot discuss that. So we are only covered the three aspects of that. So the first, the PostgreSQL architecture. So in PostgreSQL architecture, there are the three parts, actually. The main three parts are: the first is the processes, because the PostgreSQL is based on the process architecture. It's a process. When you connect to the PostgreSQL, it spawns another process, and that process is responsible for maintaining the connection with the client. So that's a process-based model. So the second aspect of that is the memory. So how PostgreSQL manage the memory, how you control the memory management of PostgreSQL. So that's the second topic. And the third is storage. That's the main thing. How PostgreSQL stores the data into the disk, in a file, in the blocks, how it stores that. So first we will discuss these three things. So here, when we are talking about the clients, if you see the left side, there are the clients. Any kind of a client, that's a PSQL, a Java client, ODBC client, or any database client which can connect to the PostgreSQL. So left side is the PostgreSQL client. And there is one process is running in background of the PostgreSQL. That's usually called a postmaster process. And that's the main process of PostgreSQL. Whenever any clients connect to the postmaster connection, it will spawn another Postgres process, and that process is responsible for dealing the connection between the client and the PostgreSQL. Like here, this is the client. So when that client connects to the postmaster will spawn another process which is called the PostgreSQL, and then the communication between client and PostgreSQL will start. So this postmaster process will again listening to the next client connection. So like this, if you have 10 clients connected to the PostgreSQL, then there will be 10 PostgreSQL processes running in the background. So there will be 10 PostgreSQL processes and 10 clients. And that postmaster connection is still listening for the new connections. So that's the process ended. If you compare that with the threading process, where one process is running and client connect to that, and another thread spawn, and that thread try to communicate with the client. No, this is not the architecture of PostgreSQL. The PostgreSQL architecture is when a client connect to the PostgreSQL, it span another process, and that process is responsible for communication between the client and the PostgreSQL. So that's the main architecture. Then there is the whole architecture. There is a shared buffer, a different kind of a buffers. So we will discuss the buffer, what these buffer are doing. So we will discuss in the next slides. So when I was talking about there is one process is running in background that's called the postmaster or PostgreSQL, and the clients have a different. Every client have one PostgreSQL process. There are some other processes are also running with PostgreSQL, and that's the process like archiver process, the logging collector, the auto vacuum, the wall writer, the BT writer, the checkpointer, the stats collector. There are all the processes also running in the background, the PostgreSQL. So that's the processes when you start PostgreSQL, the one postmaster, and these processes are running. So then you have a PG data directory. The PG data directory is the data directory where all the PostgreSQL cluster data file stores. The configuration, the data, everything is stored in the data directory. Definitely, you can create a table space outside the data directory, but the whole architecture, when you initialize the database using the initDB, that it will create a data directory, and all the data files are in data directory. So in data directory, all files are with numbers. When you create a database, you create a table, you create anything, it will generate a number for that, and that number it's called a rel file node. So that rel file node number is a file name underneath. So it represents when you have a table name, table 1, there will be a file 0000123. There is a rel file node. So the file name will be in numeric. So write ahead log, the log file is also in a pgxlog or pglog. It depends on the version of the PostgreSQL. So there is a log file. Files are also stored in there. The vol files and the log files, these are two different things. The PostgreSQL process, I already told you that when you start, there is a one PostgreSQL process, the checkpointer, background writer. These are the processes in the background. I already discussed that, so I'm not doing that again. So here, when I said that when you start PostgreSQL, you can see that three PSQL, like 3 clients are connected to the PostgreSQL. You can see that the 3 PostgreSQL processes are running, which are communicating with that. So I just cut down the processes, just show the what we required here. So there are the other processes running in the background. If you have an auto vacuum enabled, then auto vacuum launcher is there. So otherwise it's not there, so it's there. So it's all depend on that. So postmaster, the ID of that, and then other background processes. So 1 postmaster process, 3 PostgreSQL process, because we have 3 clients. So 3 PostgreSQL, 1 postmaster, and the all other processes are there. So now the PostgreSQL memory. PostgreSQL manage the main architecture of PostgreSQL managed by the whole architecture is on base the shared memories. So the main parameter is a shared buffer, where all the PostgreSQL, because this is not a client, it's not a thread-based process, where all the threads can share the heap. If you share there is a different thread, they can share the same memory area. But if this is a process-based architecture, then we need to have a shared space where all the processes can write and read data from that. So that's the shared area. So that's handling of the shared buffer, that there is a shared buffer call. So all the processes can read and write on that buffer. Definitely there are locks involved in that. So we are not going to discuss how the locks work in PostgreSQL, but there is a shared memory area. So all the processes are writing the data in the shared buffer and reading the data from the shared buffer. Similarly, there is a vol buffer, it's a write ahead log buffers, where all the vol log data is stored in the vol buffers and then goes to the disk. Then C log buffer, then the maintenance workman, the auto vacuum workman. So we will discuss that, how these we can manipulate these setting in PostgreSQL. So storage, I told you that there is a PG data directory. If you see that this is the PG data directory, and you can say the template database, the Postgres database, all the database, the objects has their own number. That's called the rel file node. And that rel file node is a number, it represents a file on a disk. So here the template database rel file node is 0. So there is a folder for that. So database PostgreSQL is a 13680. There will be a folder there. If you create a tables, then it will create 16384 is the name of the rel file node of the table admin. So there will be file for that. And these files are only 1 GB long. So if your data is more than 1 GB, then it will create another file 16384.1. So then 2 GB, 3 GB, then it will create 16384.2. So the file cannot be more than 1 GB. So it's always split up multiple files. So it will the maximum file size is 1 GB. That's the old limit, but still going on. So architecture is same that the file size will be 1 GB. So one table can have a multiple files, but donated by .1, .2, .3. I have briefly explained the architecture of PostgreSQL, how processes, memory, and storage look like in PostgreSQL. So we will discuss about the tuning parameters. There's some tuning parameters, and we will discuss about them PostgreSQL indexes, because it's also depends, can affect the performance of database. So we'll discuss. Here, I'm not talking about the query analytics because it's totally a different topic. It cannot be covered in this session. It's only whole new presentation. So again, the monitoring is also a separate talk. So the shared buffer, the wall buffer, the effective cache size, the work mem, the workload mem, and some other. PostgreSQL have a one configuration file. They have multiple configuration files, but the one major configuration file which is related to the configure the PostgreSQL, it's called postgresql.conf file. Usually, it is in the PG data directory. So you can open that file. This is a text-based file. You can open that file, and you can configure the PostgreSQL. Normally, when you download the PostgreSQL and run the PostgreSQL, PostgreSQL will start, but that will be the least performance database there. Because if you have 100 GB RAM, and the PostgreSQL will use only 128 MB of shared buffer, because the default configuration is 128 MB. So is it enough? No, because you have 100 GB and you are running PostgreSQL on 128 MB. It will run, it will create table, but it is not the optimal. Why they have done that? Because they want when somebody download PostgreSQL, it will run on bare minimum computer. If it's only a 500 MB RAM, so it should start. If the default value is 10 GB, if they try to run on the 512 MB computer, it won't run. So that's why they keep it minimum. So whenever you download, you must open the postgresql.conf file. So the major performance-related parameter in PostgreSQL is shared buffer, because all the traffic of tables and everything goes from that shared buffer. So everything, when you create a table, you insert a data, you delete a data, you select a data, it will be from the shared buffer. That's important. When it's from shared buffer, then it should be big enough to handle your queries. So by default, if you just check show shared buffer, it is only 128 MB. That's not enough. Usually the recommendation on the documentation, it's only 25% of your RAM. If you have 100 GB, then 25 GB is enough. And some documentation and some recommendation is at 40 GB. Like of 40%, like 100 GB, then 40 GB. Like if you have 40% of your RAM. So, but I am not convinced with these settings, because I have worked with the multiple vendors who are using the PostgreSQL. That's specifically when they have the database running with the shared computer. Like previously, people were running their application engine and other stuff on the same computer where their database is. So that also required the memory. They also required the RAM. If you have a dedicated computer and the RAM is dedicated for just the PostgreSQL, so why 40%? Why not 60%? What will you do with the rest of the memory? So that's because you are only running one application there, which is a database server. So try to give him the maximum, because you are not running anything on that computer except the kernel. Kernel is running, just give him some space like 10 GB, like 10%, 20%, give them. The rest you can give to the PostgreSQL. But here comes the main thing. Just keep in mind, there are multiple parameters. You have to sit down to have some calculation, because you cannot give to 90% of the shared buffer. You have some other parameters too, where you have to configure. You have to configure them too. So if you are talking about the shared buffer, the data, all the data written to the shared buffer, and that shared buffer will be written to the kernel buffer, and that kernel buffer will be written to this. That's called a double buffering. And when we are doing the Linux training section, I will explain what is the double buffering. The PostgreSQL based on a double buffering. When PostgreSQL The application writes data on the shared buffer, and the shared buffer writes data into the kernel buffer, and that kernel buffer data is written to the disk. That two buffers involved, that's called double buffering. So PostgreSQL based on the double buffering. There is a patch for the direct IO, but it's not committed yet, so we are not talking about that. We have transaction. So PostgreSQL have transactions, so you obviously using the transaction. So all the write ahead log, the log your transaction. So your transaction is logged a write ahead log. So when it's logged, it is a 16 MB with 8K blocks. This file is 16 MB and 8K blocks. So can be changed on compile time or something like that. So PostgreSQL write val is the sequence of instructions that written into val, and that instructions are written to the val buffer, and that val buffer goes to the disk. So it also depends how much you're writing the data into the log. So if it's quite frequently, then more the memory, that it's give you the benefit of that. So that's another interesting parameter. That's called effective cache size. When I'm talking about these parameters, make sure this all can be configured in PostgreSQL.conf file. There are some other systems where you can configure that, because some can be configured on the client basis, some can be configured using the alter system command, but I'm talking about when you are changing these parameters in PostgreSQL.conf file. The same applies to the other system, how you change the parameters. So when the first one was the shared buffer. So when you set any values to the shared buffer and you start your PostgreSQL, because you cannot change the shared buffer value while running the PostgreSQL. So when you change the shared buffer value and start PostgreSQL, PostgreSQL will capture that memory. That memory will not be usable for other application. That's important. So if you give the 40% of your memory of it, like the 100 GB and the 40% is the 40 GB, then this 40%, the 40 GB will be consumed by the PostgreSQL. It is not available for the other application. So, but the effective cache size is just the, it's not used by the PostgreSQL right away. It's not used by the PostgreSQL. If you said that, it's hint. It's a hint to give the planner that I have that kind of a memory and make a plan according to that. So like PostgreSQL does not know you have 100 GB of total RAM. He doesn't know, because we have not supplied that information to PostgreSQL, and PostgreSQL is not touching your operating system to get the memory sizing and everything for you. What they have done, we give them the hint that actually we have 100 GB of RAM. Make a plan that whenever you need that memory, it will be available. So this is not the value. If you said that 90 GB, so it will not allocate the 90 GB. It's just a hint for the optimizer, planner to estimate the best and calculate the best plan for that, for the faster run. So if you give you the bigger value, it will give a bigger value, and RAM is not available. Like if you give them if you have 100 GB of RAM, if you give that value to 150 GB, so it will make a plan for that, no problem. But that involves this swapping. The swap space will be used, because he has created, PostgreSQL created a plan which can use 150 GB, but there is no 150 GB available on the system. So it will be swapping involved. And if you give it too small value, like you have 100 GB and you give the value on 10 GB, 1 GB, so it will generate a plan which can only use 10 GB or 15 GB. So you have to be very careful when you're setting the value. Make sure it's not using that value right away like a shared buffer. Shared buffer is used immediately. It's no use, but this is not the value. And PostgreSQL, this is really interesting parameter. When you have on a sorting, like when you have a sorting, that PostgreSQL requires the memory where to sort the values. So if you're right and you can order by something, then PostgreSQL has to fetch the data from the disk and has to sort it. So, and this is on-demand request. It's not always. Like the shared buffer is the permanent, that is required to read and write data. But this is the on-demand request. So like it's required some 1 GB or 10 GB of RAM where it can sort and return back to the system. So it is not using the shared buffer. So for this, there is a work mem. So you can set the work mem value where your sorting will take place. But you can set that value, but keep in mind, it is not for the whole PostgreSQL. It is per process. That's really important. I have seen many database crash when they set this value quite big. They said, okay, all the processes can use this memory. No. If there are 10 clients and you set the value of 1 GB, and the 10 clients start doing the sorting, and this value is 1 GB, then total memory will be used is a 10 GB. If you have 100 clients and doing the sorting at one time, it's 100 GB. 200 GB. So you have to be careful how much sorting in parallel is going on with the processing. Like the shared buffer is the once. You created it, 40 GB, done. It started, no problem at all. But it can crash your system. It's required more and more and more memory, and one killer is there, which is called OOM. I will discuss with that, yeah, OOM, out of memory killer. There will be, it invoked and kill your PostgreSQL process because it is asking too much memory from the system, which is not available. So here is just an example that I have set. I told you I can set that value in PostgreSQL.conf file. But when I set that value to PostgreSQL.conf file, it is set permanently. So we can change that. So you can set this value specifically, on the fly for the per session base. So I just connect to the PostgreSQL and set the work mem is 2 MB. And I try to sort order by. You can see the order by ID. That means I want to sort it, and I want PostgreSQL to use only 2 MB of the memory, not more than 2 MB. So you can see the time, right? And now I set the work mem 1 GB, and you can see it's almost half the time. But the problem is if I set the 1 GB permanently, so if I have 100 clients, then 1 GB for 100, that's gone, it's finished. So your PostgreSQL will be gone. So that's really a good technique whenever you think this query will do the complex sorting. So just set that value, execute the query, reset the value to the previous value. So that's really good idea because you can set that value per session base. Another parameter is called the maintenance work memory. This is the work memory, but for the maintenance purpose. So you can set that value, like if you want to run the vacuum, that also requires the memory. But that's a maintenance task. You cannot set that value for long time that you set that value because you don't do the vacuum oftenly, because if auto vacuum is running, there is no need to run the auto vacuum time by time because auto vacuum is running. But simply the restore command, when you're creating an index, when you add a foreign key, you are an alter table. You are not doing that activity on daily basis. It's just like it's a maintenance activities. So for the maintenance activity, this is called the maintenance work mem. You can set that value anytime per session base, PostgreSQL conf, so you can set that value. Here I set the maintenance work mem to 10 MB. You can see that I just set the maintenance work mem 10 MB, and I created an index, and it took almost 12 seconds to create an index on a table. So I drop that index, I checkpoint that, and set the work mem to 1 GB. And you can see that it's only take almost 9 seconds. It doesn't depend if you set that to 2 MB, then 10 MB to 1 GB, then it should be multiplied by 10, because there is other activities too. It's not only just the memory is used, all the other things are using. So it improves. So you can think about how much it improves using that amount of memory. Maybe if I set that to 20 MB or 30 MB, I got the same results, because other RAM is unused. So it depends. It depends on the data and how unsorted data you have in the disk. The another parameter, that's synchronous commit. This is used to enforce that commit will wait val to be written on disk before returning a return success status to the client. Like if a client connect to the PostgreSQL, wait for the val to be written on a disk when it's written to the disk, and it will wait for the success or return that it will return success later. It's called like synchronous. It's the same concept of synchronous or asynchronous. It will return immediately, or it will return when the success returned by the disk, then it returns. So why this parameter is important? This parameter is important. This is trade-off. If you off or if you on, it doesn't matter. So increase reliability, decrease the performance, and vice versa. Like if synchronous commit is on, it's increase the reliability, right? Because it will go and check that it's written, it said yes, it is written, and come back. It's reliable. But is it efficient? Because 99.999% disk is okay. It's not happening the daily, the disk crash is happening. So why is always going and saying, I have written that information, I wrote that information, is it success or not? He said it's success and come back. So there, if you off that parameter, then it will go and write the data and come back. It does not wait, it's written properly or not. So we compromise a little bit of reliability, but it's not corrupt your data. It will return the information, the success or not success later. So in any case, if you go and write to the disk and disk said, I cannot write. That's a similar thing. I said to the disk, write and do some other work, and he said, I cannot write. So that's the same thing. But in one case, you are waiting for that, and in second case, you are not waiting for that. So synchronous commit does not introduce the risk of corruption. I already told it's not a corruption of data, which is really bad, but some risk of data loss. How data loss? When you go and write a data, in synchronous commit is on, and you go and write the data, and it said, okay, I have written. You have the information that data is perfectly written, but if you write a synchronous commit is off, you go and write the data and just come back and do some other work, and later it said it's not written. So you lose some information based on the assumption that data is already written or not. So that portion is the loss of data, but not the data corruption. It usually happens when it's two kind of a thing when it's happened. One, data disk is corrupted. If disk is corrupted, data is already lost if your data is corrupted. But sometimes it happens when you have mounted a remote disk on your system and you have database on that system. So it involves network, and sometimes a network glitch or something like that, it can happen. So usually when we are doing that, we usually on the synchronous commit. If you have a remote disk mounted to your disk and you have the information, the WAL files there on that disk, then turn it on, because network glitch can happen. Checkpoint timeout. I told you all the data is written on the wall and the shared buffer in the buffers, but there should be a time when all the data is written physically to the disk, not keep that information into the RAM or wall. So wall, because why we have a wall? Because wall is ensure the serializability of the data. Because you write one process is write create table, another process is saying drop database, something like that. So it should be serial, because this is the multi-processes. For multi-processes, that means parallel. But in database, there should be some seriality. So all the information is written on a serial way. Create database, create table, drop table, insert table. These all instructions are written into the wall files. And that wall files in wall buffer and the wall file. But when that information written to the disk, that's important. If all the information is keep written on the wall files, not on the disk, so what happened? There should be some time when this information is actually written to the files. I already told you the disk 001, the RHEL file node in the written. That's called a checkpoint. The first thing you can do that, write checkpoint, enter. So all the wall file information is written to the disk. So its wall file is flush and your data is written to properly on the disk. That's the one thing, but it's a manual step. You go and just write checkpoint. But you can set that time, that every week, every day, every hour, this checkpoint automatically happens. The wall files are written to the disk. So this is also a trade-off. Like if you set the checkpoints too early, like 1 hour, 30 minutes, and you have a very heavy load of data, so it's a disk spiced because it involves I/O. It will collect the data from the wall and just directly return to the disk. So it continuously spikes on the disk. So it slows down your database. But if it's too late, like you set the checkpoint for the 1 week, 2 week, what will happen? That your wall file is keep expanding. There are multiple wall files. And what happened in both the cases, if you have an early checkpoint, if you have a later checkpoint? Recovery, like your database crash, and now you want to recover your database. So if you have a checkpoint, it will do that, it will copy the files and it will replay that wall file till that checkpoint. So if your checkpoint is too early, like 1 hour before, it has to run 1 hour wall file to the system. So it's really quick. It will do the really quick. But recovery time is really quick. But if the last checkpoint is last week or last month, then it has to run the 1 week or 1 month data on to for the recovery. So quick checkpoint, slow performance, too much I/O. And the slow checkpoint, a later checkpoint, a big difference between the checkpoint, the most recovery time. So that's a trade-off. You have to figure it out when you want to have 1 day, daily 5 hours, 10 hours. It depends on database load. That's a simple parameter. That's a checkpoint completion target. That's to specify the target of the checkpoint completion as a fraction of total time between checkpoints. So its default is 0.9. So 0.9 is like which is the default is 0.9. PostgreSQL can be expected to complete each checkpoint a bit before the next casual checkpoint. So it's not occurring too often. So that's why that parameter is, if you set the 0.1, so it's a 10%, 0.2, 20%, 30%, and 90% between the time between the checkpoints. Max wall size. So maximum wall size, let the wall grow during the automatic checkpoints. So I said that when you set the checkpoint, the wall grow, so you can set the max wall size. So the default is 1 GB. How much time left? Oh, I did quickly. The PostgreSQL, that I have told you the main parameter which affects the performance the most. There are some parameter like the minor one, but you need to tweak that too. But the major one, these one, which will affect your major performance. And the other parameter, it depends upon your workload. And there are small one, it's not related to the performance, like the log file. You set the log file, where CVS log file, JSON file log file, XML log file. So it will affect some kind of a performance, but not like that. If you just set the CVS log file, it's quick, but XML, it will take a little bit more time, but it's all depend on your configuration. So when you tune your PostgreSQL, it's not just about the tuning. Why I have added the indexes in this section? The problem is that I have seen many databases where they have tuned their database perfectly. And mostly why it is perfectly tuned? Because they ask some company, they get some contract that tune our PostgreSQL. They did the tuning for them. But when they create a database, I have seen the database is badly designed, or not even the badly designed, they have not created the proper indexes on their system. And all the tuning is gone. Because if you write a query and there is no proper index on that, so what will it do? That you have a work mem, very perfectly tuned work mem, and your sorting algorithm is not working for that. So why? Why you have a work mem? You have no sorting, and you have set a perfect work mem there. So what is the purpose of that? So there is a relation between how you're writing a query and how you're tuning your database. So I just give you some example of indexes here, and then we will go to the Linux tuning. So I'm not going into detail. That the index is same index as the end of the index in the book. That same index. Database has the same index. Like book is called a table, and the end of the book there is index, and that's the index, where you have the small information and the pointer. The pointer is the page number. If you want to search some word, like I search the row level trigger, I want to see where is the row level trigger in the book. What I should do? I should read the book whole to find out where the row level trigger is. That's called a sequential scan. In table, if you want to search that row level, that's called a sequential scan. But if I go end of the book and go to the R row level, and I can see the page number 97. I just go to the 97 number page and just see row level trigger is there. That's called the indexing. If I doesn't have that index, so just imagine for one word you have to read a book every time. Whenever you want to find one thing, you have to read the whole book. But if you have an index, how much performance you get, you can imagine. So PostgreSQL have a same concept of indexing. So I'm just sequential scan. I gave you the example. That's 100% same example. Like you see, this is the table. The information is there, and you have a ID and name. And PostgreSQL have a column named CTID, and it is a hidden column. It's attached to the every row of the table. So what does that mean? It means the page or the block number on the disk and the offset. There is two things. One is the block or page number, and 0 is the offset. Where that row is. So it is the physical location of that row, but it is hidden. When you select static from admin, it will only show you the ID and name. But when you explicitly write CD ID, so it will also show you the exact location of that tuple or row there. All right? So here, CTID 10. So if I want to find where ID is equal to 8, what should I have to do? I have to go there. I have to compare ID is equal to 7 is equal to 8? No. 7 is equal to 8 is equal to 1? No. 8 is equal to 3? No. 8 is equal to 8? Yes. 8 is equal to 6? No. 8 is equal to 1? No. So 1, 2, 3, 4, 5, 6. I have a 6 rows, and I am comparing the 6 values. I am getting only the 1. Sorry, it's 8. Actually, ID is 8, so it's typo. So I have compared 6 values, just getting for the 1 value. So B-tree index. PostgreSQL have a B-tree index, hash index, gin index, gist, brin. It has a multiple index. So I'm just talking about the basic concept of indexes. If you want to see, just go to the YouTube, Percona. I have a full course of indexes is 5 to 6 hours, you can also get the certificate of that if you pass that exam. So I have detailed PostgreSQL indexes course there. It's free, just go there, pass that score, you can get the physical certificate for that. So here, B tree, if you store the data like that, so I have to compare 8. I have that 8 or not. I will compare 9 with 8. 8 is less than 9, I go to the left. 8 is less than 9, I go to the left. 8 is there. I will read that. So I will did only 3 comparison. Like previously, I did 6 comparison when there is a sequential scan. But in indexes, I did only a 3 comparison. Because data is stored like that, it's a B tree. So hash indexes, there is another index which is called the hash index. In hash index, when you store the data, it will calculate the hash for the data and store the hash in the indexes. So when you query that hash, then it will directly go to that hash and give you the value. And that index is only for the equality operator. It's not, it will not work for the less than, greater than, because hash is something random. So you cannot compare hash with less than, greater than, something like that. It's absolutely equal. So hash is only for the equality operator. B tree is for equal to, less than, greater than, and equal for all the purpose you can use the B tree. But the hash is just only for the equality operators. So I think I just gave you the idea of indexes, so you can go through these values. So how much time I have? Oh, it's only 15 minutes. So sorry about that. I will not discuss the memory architecture of Linux. So I will skip that. And just give you the idea. PostgreSQL use its own buffer, and that own buffer is written to the kernel buffer, and that kernel buffer is written to this. That is called a double buffering. If that information is directly written to disk, that's called direct I/O. If information is written to the kernel buffer and that kernel buffer written to disk, that's called a single buffering. But PostgreSQL believe on double buffering. Not believe is implemented like that. So Linux page size is 4K, right? So when you write that information, so that information is written in 4K pages like that. But modern system database, Linux have some bigger pages, and that is called the huge pages, right? Linux support that. So normally it has a 2 megabyte and 1 GB. There is no more. It's not like that you have a 2 GB, 3 GB, 4 GB. No, there is only 2 size, and more modern Linux system has a terabyte of huge pages also, but I'm not talking about that. So 4K is the normal page size, and there is another page size which is called the huge page size, which can either be 2 MB or either be 1 GB. That's it. No other value for that. So it can work parallelly. Like 4K is normal page size, and 2 MB or 1 GB huge pages, it can work together. And PostgreSQL have support for that, for the performance. So how? If you can see that, you just cat that information, you can see that you have on a Linux system has the huge pages or not. So you can see it's a 2 MB, the huge page size. So how you change the huge page size? Just go and change the grub Linux, and I set that to 1 GB, and just update your grub, shut down, restart, and your Linux will support that. But issue is not that. Issue is that huge pages are available on Linux, but to use that huge pages, you need to implement huge page concept in your application. So what is your application right now? It's a PostgreSQL. That means PostgreSQL need to support the huge pages. So how the code is there, but there is a parameter in PostgreSQL.conf file that which is called huge page is on. If your operating system support huge pages and the value of huge pages is on, all perfect performance, you will get a really good performance. your operating system does not support huge pages and huge pages is on, your database server will not start. It will say your huge pages is on, but your operating system is not supporting the huge pages. It's bummer. So if your operating system supports huge pages and the huge pages is off, then PostgreSQL will not use huge pages, regardless operating system support or not. So PostgreSQL provide another parameter which is called a try. You said huge pages is equal to try. Then when you start PostgreSQL, it will touch down the operating system. If huge pages are there, it will use it. If it's not there, it will not use it, but it will run. So usually default value is try, and you can set that try if huge pages are there or not. Okay. So then restart PostgreSQL. The most modern system has another option which is called the transparent huge pages. Transparent huge pages, what does mean the transparent? Transparent means the application, the database should not implement the huge pages concept. It will automatically use that concept. So there, any application can use that huge transparent data encryption. So 15 minutes left, 14 left here. So transparent huge pages, but the problem is that the people have observed that database is not utilizing the huge pages, transparent huge pages correctly, because that huge pages are ups and down, and operating system is managing from their end, but database not getting the benefit for that. So I have seen the blog for the MongoDB. I have seen the blog the MySQL. I have seen from the Oracle disable transparent huge pages, because you cannot disable that in your database. You have to disable that on operating system. So I have done benchmark on the huge pages. I also done a benchmark on transparent huge pages. The blogs are there in Percona. So you can see that huge pages give a really good benefit, but transparent huge pages hurt the performance. So I have seen, let's just disable the transparent huge pages because it's not beneficial for the database. So how to disable that? So I have there, you have the grub, and you can change the grub. You can enable and disable that, the transparent huge pages. How to disable that? Now, huge pages are this concept. There are some parameters, but when you are doing some fine tuning of your database, like you have done every effort for the PostgreSQL, you have done indexes, you have but you're still not getting the optimum performance of PostgreSQL, then it comes to your operating system. You need to configure some operating system value and make sure these are not PostgreSQL configuration. It is Linux configurations. You have to do the systemctl command, and you can set these value. This is the vm.swappiness. It affects the performance of the database, used to control the swappiness, right? And these values can be 0 to 100, and default is 100. So how aggressively you do the swappiness, right? Like if you set that value to 1, it will not too aggressive to do the swappiness. You mean the swappiness mean to write the data from RAM to disk and disk to RAM, to swap the data. So it controls the swappiness, right? There is problem. Somebody set that value to 0. Don't swap my data. Always use that data in RAM. What is the drawback? Anybody have a hint of that? If you set that value to 0 and the swappiness required, you're out of memory, your database will crash, right? If you set that value to 0 and there is a need of swapping, and you don't have swappiness option, so it will crash. Who will crash? There is another big thing which is called OOM, out of memory killer. It will kill it. So What people do for this value, they usually set that value to very low, like 1, 2, 3, something like that. 1, 2, 3, they set that value because it will not do the swappiness quite often, right? But whenever it requires to swap, it has that portion of memory, the percentage aggressiveness 1, 2, it will start doing the swappiness, swap the values. So at least it will not crash, but at that point it will slow down, but it will not crash. So usually people set that value to very low. If you set that value too high, because then it will do very aggressively do this swapping. That's another interesting parameter. It is called the overcommit memory. Usually what happens when your application required a memory, you write and C application, Java application, or some other application. Like I just give the example of C. Like you allocate a memory, like you said, create a pointer of 1 GB, example, right? And you have not used that memory in your code for 1 hour. After 1 hour, you start using that memory. Why you have allocated 1 GB? Okay, you did the mistake. But how kernel manage that information? When you create a memory, the kernel said, okay, I have created that memory, but it will not use it. It actually, the kernel fooled the application that I have allocated that memory for you, but it has not been created. But whenever the application required that memory, the kernel gave that memory to the application. But again, that is a problem. If that memory is not available at that time, because initially kernel fools the application that I do that. But when it's actually required, its memory is not available at that time. Boom, crash. System will crash. So there is a value. So if you want your, sorry, it's not with my ear. So you want your kernel to have an option to overcommit or not overcommit. So you have that value. So the default is heuristic overcommit. Do it intelligently. If it is required, give it, commit it, overcommit it, it's your choice. Allow overcommit anyway, but that's not a recommended value because it can cause problem. Don't overcommit beyond the overcommit ratio. That recommended value is 2 because you said that overcommit it, but if that exceeds to the overcommit ratio, then don't overcommit it. Give the error up to application immediately. So you can set these two parameters. Overcommit is good, memory is good 2, and ratio you can set that to 60%, 50% of your memory. You can overcommit or you cannot overcommit. I'm going to quickly. So there is a dirty background ratio and dirty background bytes. You can set that. So flushing is done in the background. The dirty background ratio is the percentage of memory filled with the dirty pages that need to be flushed to the disk. So you can set that value in ratio or in a bytes. So when that ratio is fulfilled and the bytes is okay, then it will flush the data into the disk. So it's also varies from 0 to 100. And that's the same value, but it's done in a foreground. It's not a background. It will stop the foreground application. So sorry about that. On the last slide, I was too fast in some slides. So it's only 5 minutes left. So I'm good to go. So if you have questions.